Hi, so this is a very special kind of combination and one that could potentially come up. So it's a mixture of our best friend, the SN formula for a geometric series, and induction. So we need to prove that Sn is equal to a 1 minus r to the n all over 1 minus r. Okay, now we've actually used this to prove things in financial maths, but how do you prove that this is actually true? We're going to use our old friend induction. Okay, so we're going to prove it for n equals 1. Prove it's true for n equals 1. Okay, so before we do that, let's actually see what this actually means. So what is our Sn formula? What's it actually telling us? Well, what's it's saying is if you take a term in a geometric sequence and you add it to the next term in the geometric sequence, and then you add that to the next term in the geometric sequence, and then you add it, keep adding it on, you'll finally get this is our geometric sequence. So what we're saying is when you add up all of these, you get this. That's what it's saying. Okay, so we're going to prove it's true for n equals 1. So let's sub in n equals 1 and see, do I get the first term? Okay, so when n equals 1, then a times 1 minus r to the power of 1 over 1 minus r. Well, as you can see, 1 minus r to the power of 1 is just 1 minus r, and 1 minus r over 1 minus r gives you a. So it's true for n equals 1. Okay, so that's your proof there for n equals 1, done and dusted. Now, let's assume it's true for n equals k, where k is an element of the natural numbers, because we're all dealing with natural numbers here. So again, what I'm saying, well, if n equals k, what I'm really saying is that if I have a sequence, a plus a r to the 1 plus a r squared plus a r to the k minus 1, that should be equal to a 1 minus r to the k all over 1 minus r. Okay, standard enough, that's all you're doing. You're just saying that that has to be true. Okay, now let's prove it's true for n equals to k plus 1, the next one in the order. So in other words, the next number after k. Okay, and of course with induction, what you're doing is if you can prove it for the next one, it must have been true for the previous one. If it's true for the previous one, you know it's true for an actual one. So if it's true for an actual one, it's obviously true for one after the actual one. So that's the kind of logic that this uses, and it's fairly solid logic. So let's have a look. Let's write out what this is going to look like. So this is going to look like a plus ar to the 1 plus ar squared plus ar to the k minus 1 plus ar, and we're going to substitute in k plus 1 for k. So that's k plus 1 minus 1. So there's the minus 1 is still there, but we're substituting k plus 1 now in for the k. And we're saying that that's going to be equal to what? A bracket 1 minus r to the k plus 1 all over 1 minus r. Okay, so this is where we're going to go. We're going to try and prove that this is true from this. If no, this is true, then that must mean that's true, and so on and so forth. So let's have a look at this and let's see where this is going to go. So I'm looking, and straight away I see that all of this can be represented by that. So that's really just a 1 minus r to the k all over 1 minus r. Okay, and this, well, let's tidy up this. Okay, I have a k plus 1 minus 1. So really that's just ar to the k. That's all you've left there. So I'm going to have to try and get this to be that. That's our prime. So let's get a common denominator. The common denominator is obviously 1 minus r. If that's the same common denominator, then I can leave this top line on as it is. This one, obviously 1, that's over 1, so visible 1 like. So that into that is just going to be ar 1 minus r, ar to the k and 1 minus r. So there I have it as one fraction. Now I need to tidy this up and make it a little bit nicer. So let's just multiply everything out. I think if we multiply everything out, things will look a bit better. A times 1 is just a. Again, this is all over 1 minus r. A times 1 is A minus A to the rk plus 1 A to the r, A to the rk. And then we have minus A to the rk, A to the rk by r. Okay, so what I can see is that everything there has an A, just like everything there has an A. So I can factorize A out of the top line. So A, let's see what I'm left with. 1, A into A goes once, minus r to the k plus r to the k. And then if I take the A out of that, I'm left with a minus r to the k by r. Nearly there. Two more lines should do it. 1 minus r, still have our A, a minus r to the k and a plus r to the k, they're gone. So I'm left with 1. And then let's use our indice rules. When you have two base numbers, you can add the indices. The indice on that is k, the indice on that is a 1, r to the k plus 1. And is that? That it is. So it's true for n equal k plus 1. Therefore, it's true for n equal to k. And if it's true for n equal to 1, it must be true for n equal to 2, etc. And there you have it proved. Okay, I'd hope that would come up for you, because while it looks scary, it's actually lovely. I think it's nicer than the Invisibly one.